Welcome to another video for Lambda class. In this video, we're going to discuss equivalence relations. Well, equivalence relations are a very useful device for identifying objects. And also they provide us a way of building new sets out of given ones. So let's try to express this in terms of set theory. Okay, so we need to learn what a relation is first. So let's start with a definition. Let A be a non-empty set. Okay, it can be finite, it can be infinite, it doesn't really matter for our purposes. A relation on A is a subset of A times A. So this is what we call the Cartesian product. Okay, let's give some examples. Okay, examples. First example, let's choose a finite set. 1, 2, A, and T. Okay, so this is a finite set. It consists of the elements 1, 2, A, and T. What is the Cartesian product? Well, that product is simply the order pairs. It can be described as the set of pairs x and y such that x and y belong to A. In this case, since A is finite, then the square or the Cartesian product is also finite. And in this case, we can actually list what A times A is. And we are, it's simply a matter of displaying the elements one by one. In this case, 1, comma 1, then we have 1, comma 2, 1, comma A, and 1, comma T. These pairs belong to the square, right? So then you have the pairs beginning with 2. So the pair 2, 1, pair 2, 2, pair 2A, and the pair 2T, right? Let's put a semicolon there. And then you have the pairs beginning with A1, A2, AA, and AT, and finally the ones that begin with T, right? T2, TA, and finally TT. In this case, we were able to describe the Cartesian product simply by listing all its pairs, right? And this is the whole A times A, right? So what is a relation on A? It's a subset of A times A. A relation on A is a subset of A times A. For instance, we could say that we have this pair, we have this one, and also maybe A and 2, and then T and T. So from the whole of A times A, we just select a subset. Yes, I changed over there. Okay, so R is a subset of A times A, the Cartesian product of A with itself. It's actually choosing this element, this element, uh, this element, and this element. That's simply a relation. Sometimes relations can be expressed not enumerating its elements, but by a rule. We can also have that kind of description of a relation. So let's go for another example. Let's try this time the real numbers. Okay, so the set that we choose to work with is the real numbers. And what is A times A? What's the Cartesian product of A times itself? Well, that's R times R, or what we know also as R squared, pairs of real numbers. In this case, the folklore is that we represent R squared with Cartesian axis. So we usually write this graph or this picture just to see R squared. So what is a relation on A? A subset of R squared. Let's say we can describe the relation maybe with a condition. It's the pairs of R squared such that y equals x squared. In this case, that shows that the relation itself is a subset of R squared and can be depicted as a parabola that has its vertex at the origin, right? So this is a relation on A. It's a subset of the square A times A. It's a very flexible concept. But we're interested in equivalence relations. So what is an equivalence relation? Well, it's going to be a relation that satisfies some extra conditions, right? And those conditions are not very complicated to understand. Definition, let A be a non-empty set and R a relation on A. We say that R is an equivalence relation if, first of all, for each A belonging to A, then A times A, or the pair A comma A, belongs to the relation R. sometimes we're going to mention this property with a different name. Then each time the pair AB belongs to R, then the pair BA also belongs to R. And lastly, if A comma B belongs to R and B comma C belongs to R, then A comma C also belongs to R, right? So these three conditions define what an equivalence relation is. Conditions 1 to 3 go by their own names. A relation that satisfies the first condition is called reflexive. So this is reflexivity. Okay, a relation that satisfies condition number 2 has a kind of symmetry condition, so this is symmetry. Okay, and a relation that satisfies number 3 is what we call a transitive relation. So this is transitivity. So this is what a equivalence relation is. It's a relation that's reflexive, symmetric, and transitive, right? So this is what a relation needs to verify in order to qualify as an equivalence. Okay, so maybe we can decide if certain relations are actually equivalences just by looking at these conditions 1 to 3, if they're satisfied or not. So let's try some examples. Okay, so from some minutes ago, we have the set A consisting of 1, 2, A, and T, and we had the relation consisting of the pairs 1, 1, 1, 2, I guess it was A2 and TT. A2 and also the pair TT, right? So we need to see if this relation R that we are exhibiting here has the property of reflexivity, symmetry, or transitivity. Okay, so we need to check if R is reflexive. So that's our first question. We ask, is R reflexive? Well, it contains the pair 1, 1. So that's good. But it doesn't contain the pair 2, 2. It needs to be there in order to be reflective, right? For each element of the original set, the element has to be related to itself. In this case, 2 is not related to 2 because it does not belong to R. Then the relation R is not reflexive, so R cannot be an equivalence. Okay, so this one is not satisfying reflexivity. Let's try a different one. Let's try um, this time. Let's try the integers z, and let's define r as the pairs x and y belonging to z square, such that um, y minus x is greater or equal to 0, right? So R is a subset of the square set times set. So we are asking is R reflective? Okay, so we need to check if contains the pairs of the form k comma k for each k in Z. For k in Z, then k minus k is equal to 0, which is greater or equal to 0. So this means that the pair kk actually belongs to R. So we have proved that if we pick an integer, then the pair k times k belongs to R. And this is valid for every k in Z, so R is reflective. Okay, so we are dealing now with a relation that's actually reflective. Then we need to check symmetry. Is it true that this is a symmetric relation? So now we are asking if R is symmetric. Is R symmetric? And okay, let's take an element in R. So 1, 2. So 1, 2 belongs to R because 2 minus 1 is 1, and that's greater than 0. Okay, so this means that 1 is related to 2. But what happens when we take the opposite pair? Okay, so we see that 2, 1 does not belong to R because 1 minus 2, that's negative 1, that's less than 0. So in this case, we have a relation that's reflective, but it's not symmetric. It contains this pair, but it doesn't contain this other one. So this says that R is not symmetric, and this means that R cannot be an equivalence. Okay? Let's try a different one. Let's try a more exotic one, maybe. 3. Let's choose A, the English dictionary. So this means that our set A consists of all the words in the English language, okay? And we will define a relation this way. It consists of the pairs such that x and y have the same number of letters. Okay, so in this case, car and sun are related. Okay, also sun and sun are related. Okay, and say house and car do not belong to R. Okay, these two words have different number of letters, so the pair house comma car does not belong to R. Okay, so we need to see if R is actually a equivalence relation. Well, this is fairly obvious at this point. R is obviously reflective. Each word has the same number of letters as itself. It's also symmetric, and it's also transitive. So in this case, R is an equivalence relation. Sometimes relations are described by complicated equations or maybe inequalities, but the fact of being reflexive, symmetric, and transitive allows us to see R as a way of refining the original set. Okay, we'll just write some notation and we'll see what it produces. Observation. Let's talk notation. Let A be a non-empty set and R an equivalence relation on A. Well, first of all, what we are going to say now is how do we use this language in a more practical way. Sometimes when we want to say that the pair x comma y belongs to the relation, we will say that x is related to y. And we use this notation instead of the order pair one. So this means that x is related to y through the relation R. And we read this just like that. X is related to y via R. Okay? Simply, when R is understood, we just say x is related to y. Okay? Definition. As before, let A be a non-empty set and R a equivalence relation on A. Okay, we are going to define, let X be an element of A. So we're defining X hat, which is a set. It's the set Y of elements of A such that Y is related to X. This is what we call the equivalence class of X. Sometimes we'll just write C sub X, or sometimes we're going to write X between brackets. All these are similar notations, but what's important here is that this is a set. The set of all elements of A which are related to X. So first of all, this set is non-empty, right? Observation for X belonging to A. The equivalence class of X is non-empty. Because X itself belongs to its equivalence class. This happens because R being an equivalence, this guarantees that X is related to itself. So this means that X belongs to its own equivalence class. So equivalence classes are non-empty, okay? Are non-empty. And then what we are going to see is that equivalence classes help us refine or simplify the original set. Let's take a look. Let's take a look at this. Suppose that you have an original set called A, and here lies X. And for some reason you determine that all the ones that are related to X lie here. Okay, so all these green ones are the ones that are related to X. Okay, so this subset of A is actually X bar. Then say you have another element Y, and these guys are the ones that are related to Y, the ones that we paint with light blue. Okay? And finally say that you have an element T, which has all these guys related to it, the guys in red. Okay, so this ends up being the class of Y, and this ends up being the class of T. We have partitioned A as a disjoint union. If we join, or if we take the union of these three sets, we'll recover the original set A. And this is a very distinctive feature of equivalence relations. Equivalence relations allow us to form a partition of the original set. And in some sense, we can think of A through the lenses of R. We can think of A by the lenses of R, and this consists of only three equivalence classes. So an equivalence relation allows us to think as A being a union of disjoint sets, or thinking of A through the lenses of R as having only three elements. We're going to go deeper into this aspect, and first we need to prove that given an equivalence relation we can always do this what we're looking at now. So we need a theorem, and that's what we're going to prove now. Theorem. Let A be a non-empty set and R an equivalence relation. All right. So first of all, we're going to prove the following. If X is related to Y, then they have the same equivalence class. Right? That's the first thing we need to prove. And then we're going to prove that A can be written as a union of equivalence classes. Okay, so these sets that are indexed but by A is actually a disjoint union. So let's prove the first statement. Okay, so we need to prove the first thing. So let X be related to Y. We need to show that the set of things related to X is actually the same set of the set of elements of A that are related to Y. So we need to show this. This is showing that two sets are the same. Sets coincide. So whenever we want to show that two sets are the same, we need to show that one is contained in the other one and vice versa. Let's show that under this condition, then the equivalence class of X is contained in the equivalence class of Y. And to show this, we need to say the following. We are going to take an element of the set and we're going to show that it belongs to this set. We are going to take an element of X bar, and we're going to show that it also belongs to the class of Y. So this is what we're going to do. Let A belong to the class of X, So this means that A is related to X. Since by hypothesis X is related to Y, then transitivity ensures that A is related to Y. That's what transitivity does. If A is related to X and X is related to Y, then A is also related to Y. But since A is related to Y, then A belongs to the equivalence class of A, of Y. So this shows that since A belonging to the class of X was a typical element, this argument holds for every element in the class of X. So every element in the class of X belongs to the class of Y. Okay? If we want to prove the reverse containment, we just do the same. And we also need to use symmetry. Let B belong to the class of Y, and we need to show that it belongs to the class of X. So this means that B is related to Y, X related to Y implies that Y is related to X, and now this is possible because of symmetry. Okay, R is symmetric, so whenever we have these two guys related in this way, we also have these two guys relating in this way. And now we use transitivity. B related to Y and Y related to X. That means that B is related to Y. To X, I'm sorry. So this is that B belongs to the class of X, and since B was a typical element of the class of Y, then what we have is that the class of Y is contained in the class of X. So the double containment actually means that the classes are the same. They share all its elements. Okay, so in this sense, we're going to make an observation here. X and Y are both valid representatives of the class of X. We can say that X and also Y represent the class of X. In this sense, X and Y are somehow melted together in the eyes of R. Now you can say that it's the same class, right? So we have proved assertion number one. If two things are related, then they have the same equivalence class. And then we're going to show that A can be expressed as a disjoint union of equivalence classes. So we're going to show it number two. So let's try to break this down a little bit. So since the classes are non-empty, take A belonging to the set A, then A belongs to its own equivalence class. So what we have now is that the element A belonging to this set is in one of these guys. Okay, so A is actually contained in the union of all the equivalence classes. Okay, but now every equivalence class is actually a subset of A. So this is a union of subsets of A. Then when you take the union, what you get is another subset of A. And this shows that we have an equality here. And this shows what we needed to show. A can be expressed as a union of equivalence classes. Okay? And this union is disjoint. Observation. This is a disjoint union. There's no overlapping. So you have the class of X, and then you have the class of Y. Okay? If X and Y happen to be related, then the class of Y is actually the class of X. So this is a disjoint union. This is very important because what we have seen now is that every time that we have an equivalence relation, we get a partition of the original set. It also works in the reverse order. If we have a partition, then we have an equivalence relation given by that partition. Observation. If pi is a collection of subsets, 3 is a partition of A, which means that A can be written as the union of those sets. Then pi defines an equivalence relation in A. By simply putting, okay, we're gonna declare that X and Y are related through pi if and only if X and Y belong to the same piece of J. So this gives us another way of defining equivalence relations through partitions. And maybe this helps us to talk about one of the most important ones. We'll see an example now. The integers, and we're gonna let's fix a natural number n, and we're gonna say the following: X is related to Y if and only if x minus y is divisible by n. Okay, so this gives us a partition of A into disjoint sets. Okay, so let's take a look for n equals 3. Right, so to be concrete, let's use n equals to 3 here. So let's take a look at the class of number 0. This consists of all the integers such that y is related to 0. So this means we're talking about all the integers such that y minus 0 is divisible by 3. If we need to make a list, it will be a never-ending one, but we can actually see what it is. It's the multiplication table for 3, right? Then we can take a look for 1, right? So this is the set of all the integers such that y minus 1 is divisible by 3. So we can make a list. 1, 4, 7, 10, then you have 13, then you have 16, and so on. Each of these guys, when you subtract 1, then you get a number that is divisible by 3. 1 minus 1, 0, 4 minus 1 is 3, 7 minus 1 is 6, 10 minus 1 is 9, and so on. And then you have the class of number 2. It's the collection of integers such that y minus 2 is divisible by 3. So it's a collection of numbers such that every time you subtract 2, then you get a number that's divisible by 3. And, well, you have, for instance, minus 4, minus 1, then you have 2, then you have 5, 8, 11, and so on. Right? It happens that the whole set of integers can be thought of as the union of these equivalence classes that are disjoint sets. We have written the integers as the union of equivalence classes. But more importantly, what we can do now is we can take a look at the integers modulo 3. We can say, okay, we're going to take a look at the integers, but through the equivalence relation, the difference being divisible by 3. And then what you have is a set formed by the equivalence classes. This quotient is also known as the quotient of A by the relation R. Sometimes it's written like this, and it's also called the quotient set. The quotient set has elements being the equivalence classes. And in this sense, we need to understand that we are transforming an infinite set as the integers into a finite set. It's like being able to see 3 categories of integers. The ones that have a remainder 0, the ones that have remainder 1, and the ones that have remainder 2 when you divide them by 3. So this operation of taking a look at a set through the eyes of an equivalence relation is extremely important in mathematics. It's a way of discerning and a way of classifying objects. It needs to be noted that this quotient is a new set. This is a new set with 3 elements. The quotient is a new set with 3 elements in this case. Okay, so it's not always the case that we get a quotient with finite elements. We can also get quotients with infinite number of elements. And we're going to explore what happens when we get a finite set, especially with the integers. Sometimes observation, in this case, we also get a different notation that's going to be very, very familiar for us. This is also noted sets of 3, the integers modulo 3. We're going to explore that this equivalence relation, this definition that we gave here, has lots of other properties. Namely, it's compatible with the operations with the integers. So the operation of transforming the original set into the quotient set has more properties than simply being a function. Okay, so we're going to leave that for the next video, and well, I hope you enjoyed this. You can watch this as many times as you want. Hopefully the following videos will make clear whatever needed to be clarified. But this is a very important concept in mathematics. Okay, so until the next video, goodbye.